So it is my pleasure to introduce Bill Tang, who is going to give today's seminar on deep learning acceleration of progress in fusion energy research. Bill's been in a part of the fusion community by decades,
yes,
longer than I've been in particle physics, probably. And in the last 10-ish years,
yes.
has worked on a problem that is germane, especially for the future of fusion instrumentation. And that is to figure out how to avoid the plasma instabilities killing the instrumentation. And he will tell us all about this in today's seminar. And I'll give it all to you.
Great. Thank you very much, Frank. I'm grateful for Frank's hospitality and setting this up, and Rafi Nazikian from General Atomics for coordinating this with Frank. This is a really exciting time for clean energy fusion development. And it's also a time where the opportunities are really great for bringing aboard AI for science type capabilities into accelerating progress. So I'm very happy to talk about this today. So this is my kind of a opening slide that talks about what is the situation analysis. The enthusiasm, progress, and prospects for fusion energy has seldom been better, and the reasons are as follows. The recent announcements in Europe of the largest existing fusion experiment, the Eurofusion Joint European Torus device that's situated in the UK, had achieved 5 seconds of confinement time for ITER-relevant deuterium-tritium results. And this was announced in February 2022. This is a big deal because this showed that you could actually hold this hot thermonuclear plasma for 5 seconds, and never been done before. And so the European ministers and such all were very enthusiastic about this, and it translated to what happened in the US's reception about this, because the challenge for delivering clean energy for the world is a big deal, as everybody knows, with the present world situations. And Secretary of Energy Jennifer Granholm launched a very aggressive initiative called Developing a Bold Decadal Vision for Commercial Fusion Energy. And she announced this widely advertised activity in March of 2022. And close to the same time, you know, the Chinese, there's plenty of international competition in this area. I mentioned Europe, also Japan and Russia, and they're all part of this big consortium to deliver clean energy fusion. The Chinese in particular are very aggressive moving forward. They have very powerful technological capabilities. They're very deeply engaged in AI and such, and they have targeted fusion engineering test reactor by the mid-2030s, 2035. And that's the same time scale that Secretary Granholm would really like to see the pace accelerated in the US. But how are you going to do this? So the scientific goal is to achieve the so-called Lawson criterion that's been around forever, since the 1950s or so. Basically, this requires that to deliver a burning plasma that could lead to viable power plant design, with tokamaks, as the tokamaks are these donut-shaped magnetic confinement systems that have been around in a well-established way since the early 60s. And it clearly remains the leading approach towards ignition. That means igniting the thermonuclear plasma fuel. But you have to ignite the plasma, and you also have to confine it, because other approaches like the stockpile stewardship-driven laser plasma interaction and confinement, there's been exciting developments there too, and they achieve ignition. That's been demonstrated, but confinement is the big challenge there. And so here, the magnetic fusion area has really given probably the most viable sort of track forward in this area. The associated requirement is that you have to deliver practical operations workflows, and you do this with high performance computing, artificial intelligence, and to be able to handle large amounts of data, both measured data as well as simulated data, and to achieve the scientific objectives in a scale of project for enabling future forecasts. And this whole category where fusion energy, the grand challenge in this area, is one of the key areas, but there's many others. AI for science, series of simulations that involves inference training and so forth, is pretty widely advocated these days. The National Science Foundation in particular has launched quite a few of these AI for science centers already. DOE has not quite gotten up to speed on that yet, but they are very actively doing this this past summer in terms of identifying the immediate objectives. Our objectives meaning what are the key obstacles and gaps confronting the timely R&D progress in this area, in this AI for science area. And this U.S. Department of Energy series of AI for science and security meetings, which happened this summer, because the web link is shown below. I attended two or three of these meetings. They were quite stimulating. These are all invitation only meetings involving up to 300 people, scientists that were that represented all of the DOE national labs. And but a little backing up a little bit, what do we mean by validated advanced scientific HPC, et cetera? Because you're focusing on this because as everybody understands, this gives you a measure of the state of understanding of natural and engineered systems. So pedagogically, if you look at this sort of thing, you start off with the theory, big data type, mathematical statistical models, and then you develop them with cross-disciplinary effort involving computer science, applied math, and computational physics. You deliver computational predictions, and then what's the rest of this sort of a cartoon here? On the left side here, this is sort of the validation loop where you have VV and uncertainty quantification, and you test your models throughout that loop. What do you do with that? Well, you do comparisons. You take a look at empirical extrapolation. You look at sensitivity studies, detailed spectra, correlation function measurements, and you keep on going through this loop until you're satisfied that you have some level of agreement with observational experiments. But the other part of this curve here, this cartoon that I drew here, is that the performance loop, because practically you can't take a month of Sundays to figure out how to do all of this. So you have to exercise testing the speed and efficiency of these HPC codes. And so this is what I label the performance loop here. And so these involve so-called modern co-design challenges, low memory, core locality, latency, and so forth. And so this, you also go through this loop repeatedly until everything is moving forward in a reasonably timely way. In other words, it doesn't take you a long time to do this. And so satisfying the observational benchmarks, at least at a certain level, and the performance criteria, then you repeat the cycle as new phenomena is encountered, and this is what the validated scientific codes do. And coming back to what we talked about, the grand challenge for fusion is to follow this ITER goal. ITER is this at least $25 billion facility located in France. It involves 7 governments representing over half the world's population. And it's a dramatic next step for magnetic fusion energy, producing a sustained burning plasma with first plasma. This is like just a kickoff plasma targeted for, it's been delayed now to about 2028 because of supply chain issues and very unfortunately, Director General Bigot passed away. And so there's a lot of things that caused this delay. And what's the goal here? The Eurofusion Joint European Torus has achieved 10 megawatts of and held it for a second with a gain of order unity. The ITER goal is to go to 500 megawatts, hold it for over 400 seconds with a gain greater than 10. And when people ask me, well, what roughly does this mean? This means that basically, if you draw an analogy with aviation, this is analogous to what the Wright brothers achieved at Kitty Hawk. The damn plane will fly. And if that's the case, then it's very unlikely that all of the consortium, international consortium, will stay collaborative. Some of it will, but others will not, because they will have the confidence to move forward. So the highest priority is to predict and control the sort of physical events that can cause this thermonuclear plasma to fly apart. And these are called disruptions. And you have to predict and control these disruptions and in order to make ITER successful. And so realistic artificial intelligence enabled HPC simulations are absolutely required to cost effectively plan, steer, and harvest the key information from very expensive. Every shot's going to be expensive. It's going to cost over $1 million per long pulse to run. And the ITER shots will enable a pathway to a demonstration power plant at the next level. It won't necessarily look anything like ITER, and enable confidence and a more rapid pathway to a so-called fusion power plant. And that's what Secretary Granholm was really pushing the US to really get engaged in and move forward on. And so why AI? AI machine learning is a really essential ingredient for enabling these ITER goals to happen, and a first-of-a-kind pilot plant that we've been talking about. And what do you mean by some of the AI machine learning sorts of things? And here you can see an illustration of this. Across the top, these technicolor boxes are, you have to identify the signals that are measured. These are physical signals, density, temperature, radiation levels, and so forth. And you have to pre-process and extract the key physics features from them to make this workflow. You normalize everything to a numerical scale of order unity. These are all database with all signals divided by their standard deviation. And then this is where the AI part comes in order to train the models, in order to carry out the predictions accurately and with high speed. You have to exercise hyperparameter tuning. This is using high-performance supercomputers to enable you to better train the model. So all of the available data, I'll pause a little bit here to say what this is involved. All of the available data is analyzed, and the first approach is the so-called long short-term memory network, which is exercised iteratively. Then to keep track of how you're doing on this, you track this by looking at these receiver operating characteristics, which are plotted. It tells you how whether you're coming close to what you're achieving in a timely way, and cross-validation of the losses for every epoch or equivalent of an entire data set for each iteration. So this is what you do, and there's a lot of literature written about this, and then you use the model for prediction. And then you move forward, and you're constantly upgrading this as you go forward. This is work that we did at Princeton that had a pretty strong impact, because in predicting disruptive instabilities in controlled fusion plasmas through deep learning. And this was published in Nature in April 2019, and basically involved deployment of these convolutional recurrent neural network components and assembled together in a very efficient way. Again, you absolutely needed supercomputers to help you do this, for integrating both the spatial and temporal data to predict the Tokamak plasma disruptions with unprecedented accuracy, speed, and transferability. What do I mean by transferability? Well, before I get to that, this is a picture here of a disruption. This is this glowing part right here. This is from the jet experiment. If I had more time, I would actually run a little movie that actually depicts what happened in a disruption of jet. And you can hear the loud, thunderous roar of when a disruption happens. But then right below it is really, if you're measuring, you're not just focusing on when that disruption happens. You want to, it's sort of like analyzing a patient. You don't want to wait until they're ready to kick the bucket. You have to make sure that the plasma state that's evolving is reasonably well behaved, and that's what's shown here. The top plot here is a measure. You can't see it real clearly, but these are measurements, diagnostic measurements in a thermonuclear plasma that are time traces, temporal traces, magnitude only. They just focusing on that, and that's what the Eurofusion jet people did for a long time before we got involved in this, because they had a hard time doing this next panel thing here, which shows the spatial signals. These are measurements of the one-dimensional profiles across the plasma. So what we did in the Nature paper was to be able to combine these things, concatenate both the 1D and the 0D signals. And this is with this recurrent neural network that I just talked about. And the bottom plot here just shows as a function of time leading up to this, like when a disruption is about to kick off. This is all you're tracking this all along and tracking what, this movement towards this alarm threshold. And this is just a cartoon that's reproduced in the Nature paper. And what are the key achievements? Why was this important? Why did Nature publish it? And they asked some good questions about it, and basically, with the aid of the General Atomics people here that shared their large amount of accumulated data on the D3D facility, which is the only fusion facility producing results in the US. And then, of course, the big Eurofusion jet project. And so one of the things that the Nature editor said is can you clearly validate this ability to deal with the one-dimensional physics signals that the jet people had a hard time with, and to demonstrate a significant improvement where that beyond what other people had done, which is scalar only 0D signals. You had to be able to incorporate more of the physics world into it. And so we were able to do that, in concatenating both the 0D and 1D signals. And we also, it was also represented first demonstration of a crucially needed transferability, transfer learning. What do I mean by this? In simple terms, it just says the capability for predictive software that's trained on one experimental device like the D3D Tokamak. It must be able to make accurate predictions on another one that, for example, the much larger, more powerful jet system. And it's a key requirement for E to relevance, because if you could only do it on one machine and you couldn't demonstrate this transfer learning, then most of the experimentalists and the control people don't really want much to interact with you about, because this is absolutely required to be the case, and it kind of opens the door for you to be able to attract a lot more other facilities like the Japanese facilities and the ones in other parts of the world, and you can make use of all of this data. And here's where the third bullet down here is that in this Nature paper, this is the other major reason, in addition to transfer learning, that the editors of Nature really were keen to publish this paper. It was a unique demonstration of the AI deep learning capability to efficiently utilize these leadership class supercomputers to train predictive software. And this was done, I won't go into all of this, but for the Summit facility at Oak Ridge National Lab with the Tsubame machine in Japan, and the emerging powerful systems, which included, now we have the Exascale frontier system, which is the new #1 worldwide system, the AURORA system that Intel is pushing forward, and prior to Frontier's arrival, Fugaku was the Riken entry into all of this. This is the Japanese national facility. It was #1 worldwide in 2021. And so everything keeps on moving forward and the technology keeps on getting better. So, and so it gives you more hope that these capabilities that need to be developed can be developed in a timely way. So now what's happened since our 2019 paper? We put a lot of emphasis into translating this into real-time advances. Plus, and this is something that's really quite interesting, that, you know, in the business world and other applications, people will say, yeah, great, you know, machine learning, AI works fine, but do you have any real understanding of why? And so we took some time in this International Atomic Energy Agency paper, which is reproduced in this archive print. And so what basically did this involve? This involved, we put some work into taking what was developed in that Nature paper and being able to adapt it to make it usable in a real-time plasma control system at General Atomics here. And so specifically what happened? Well, during the General Atomics D3D Tokamak startup phase that involved over 200 shots in the May-June 2020 timeframe, what we call this fusion recurrent neural network inference engine was shown to be readily functional during real-time operations. So we're very encouraged by that. And in addition, the characteristic execution time for this inference engine to be functional was less than a couple of milliseconds. And these were achieved in line with typical operating times for the plasma control system actuators. What are these? These are like the operations of, if you're trying to adjust the plasma state. Remember, as I said, you don't want to always be dealing with a sick patient before the patient's ready to kick the bucket. You want to be able to treat that patient earlier. And so you do this with feedback actuators on a proper time scale to adjust the plasma state. And this was a really exciting sort of development in the D3D plasma control system that showed that you could do this. You could be exercising, if you will, the arms of the robot that will enable you to go to a better plasma state. So it sets the stage for systematic actuator testing, targeting the demonstration, the ability to actually modify the plasma state to avoid or delay the onset of disruptions. And from a physics standpoint, this basically says that you're moving to a more favorable thermodynamic state, where you're not going to eliminate all free energy drives in there, but you're moving the accessibility condition of this free energy thermodynamically to a more favorable state. So the magnetic trap holds the thermonuclear plasma for a longer time. So this is a big challenge, and it's something you want to do. Now, this is the other thing that came out of our work that drew a lot of attention, is that these inference engines were able to distinguish different so-called disruptive from non-disruptive tearing modes. What are these things? These are, not to get into all the details about it, but this is like the evolution of the plasma. Remember, we showed these sorts of panels. This is the evolution of the magnitude only of all of these time traces of all these signals, so that you can't see real clearly. And this is the actual profile measurements. And what we were able to demonstrate here is that you can distinguish, and these are actual D3D shot with specific shot numbers here. It basically shows that you can distinguish these cases where these are the precursors, if you will, for if you have these tearing modes or neoclassical tearing modes, this is sort of a harbinger, if you will, that a disruption will follow very soon. And so you want to be able to detect this and be able to predict this and distinguish this. And we were very happy we were able to do that. And so this was a featured result in this IAEA paper. And this is the other part that I mentioned. When people ask the question, not necessarily the business world people, but the scientists will always say, well, fine, maybe it can give you some nice practical results in terms of the predictions and such, but do you have any understanding from it? What kind of physics information do you gain from this? And so we took some time to try to do that here. So the contributions of the physics-based signals, which are lined up over here, all these different, these internal inductance, plasma current, so-called other phenomena that are measured. And if you trace this as a function of time, you can see, these signals getting stronger and stronger as you approach a disruption. And so this evolution, if you will, the sensitivity score of specific shots that came out of D3D is very, very important because it gives us a nice feeling for why the predictions that you're able to execute actually mean something with respect to these physically measured quantities. So to repeat, the key points from this IAEA paper is that we achieved integration of the AI deep learning predictor into an actual plasma control system. Plus, we carried out statistical sensitivity studies with real-time actionable integration that you just looked at. So when more signals are included in the training database, you were able to improve the physics-based predictive capability delivered because you have a better feel for what you're manipulating in terms there's a whole plethora of different arms of the robot, if you will, but which ones seem to have the best effect in giving you better performance. So this FRNN inference engine, as I said earlier, it operates on timescales needed for real-time actuator engagement to impact the plasma state. And the motivation for ongoing studies into real-time deep learning sensitivity studies is very well motivated to enable us to do this better and better moving forward. So in order to do this, remember all this machine learning AI sort of work here, you have to have access to a lot of data. And as I said before, for the most part, these are, ground truth measurements of the actual signals for the density, temperature, radiation, current, so forth. And you have to execute this in a sufficiently rapid way with workflows to support the fusion experiments and to facilitate the data for AI machine learning. And so, working closely with Dr. Nazikian, our colleague here, we were able to persuade the DOE funding people from both the Fusion Office and the Office of Advanced Scientific Computing Research to enable us to launch a program just this year that enabled us to do this. The challenge here is that scientists and the machine operators in control rooms have 20 minutes or less to decide what to do before a next discharge. And so how are you going to do this? How are you going to do this efficiently? Well, the real-time results from advanced workflows can help answer this. In particular, one of the things that you have to be able to deal with are so-called anomalous events. These are kind of unexpected events, like a tile falling down or something. These are real events. You have to still deal with it. And so you have to have a system that can respond to this. So it advises you on the adjustments of what experimental parameters need to be tweaked in order to keep things going. In other words, stop and go signal for continuing the experiment. You have to do all of this. So you need to quickly process the data and use AI at scale to locate and analyze what these anomalies might be, as well as the more natural events. You compare against simulations, and you deliver AI recommended actions to do something about this. And this shows the control room and such. And the data outside that used for training and designing such as system failures, as I said, tile falling in and things like that. You have to react to all of that. And the people at the nurse facility in Berkeley, and of course D3D, which is the only machine that's producing real fusion data right now, put together a compelling proposal that was funded. And the most compelling argument was that we are able to promise with good confidence that if you fund this activity, we can move beyond business as usual. And people say, oh yeah, of course you want to be able to couple data producing experiment with a high performance computing facility, and doing this with these two fusion and DOE Oscar activities was a natural thing to happen. And so to be a little bit more specific here, we also exercise in our proposal here a consistent automatic kinetic equilibrium fitting analysis for use that's used for validation and training of machine learning models. This well-established EFIT software just evolves the equilibrium state and as a temporally, and it allows you to adjust some of these actuators that we're talking about, and the models are continually being improved. And so a robust workflow for analyses previously done manually. That's why I say, welcome to the 21st century. We have to be moving forward on these things. So you have to generate self-consistent, high-quality equilibrium profile sources and transport data to be run for all of these D3D shots, and results saved using this MDS Plus tool that is well established. Extensive high-quality databases are they're like gold, because this is really needed for validation and training machine learning. This CAKE automated kinetic EFIT software will be used as you further improve this EFIT with AI capabilities, training on the equilibrium reconstruction shown in these cartoons here. And this is a very productive, active collaboration involving Princeton University, General Atomics, and the Nurse Supercomputing Center. And it's EFIT AI trained on 340 plus magnetic equilibria compares very well with EFIT calculations, and it takes a fraction of the time. So it's very easy to demonstrate how efficient this can be. So coupling the fusion facility operations and data for HPC computing is an essential next step for fusion and for AI. And it's really fortunate that we have this ability to do so here. This is the experiment at Princeton, which is still not functioning, but D3D's National Fusion Facility is doing very well. And then, of course, moving forward, ITER in France with the US as an active partner is shown here. And here are the different pieces of hardware capabilities, including Perlmutter, which is the main supercomputing facility up the road in Berkeley. And so this is a very demonstrable activity that's moving forward. And I pause for a second and say here, this is also a really exciting opportunity because, historically, this place, the San Diego Supercomputing Center, took its origins in dealing with fusion data as a supporting computational resource for fusion. And time evolved. I won't get into all of that, but now it's a prime NSF supercomputing facility. But you're right on the doorstep of the data producing facility, and it makes every sense to try to develop strong collaborative interactions that I think in the past where there might have been some hesitation before, both the Department of Energy and NSF would look to this as an interesting and a positive opportunity. So let's move forward a little bit here. So what I've been talking about here is facilitating data, meaning observational measured data for the most part. But there's also very, very important simulated data. And simulated data comes from various sources. And here's a nice, this was a nice paper that was published on this GTC, or Global Particle and Cell Code, that came out in Science. That was the first widely recognized HPC discovery science paper in plasma physics. And this science paper was, it's arguably just almost as hard as to publish as in Nature, but it made some very, very interesting predictions using HPC. But the issue with using this, which is this particular, its code has moved from electrostatic to fully electromagnetic signals and be able to deal with more complex geometry and such. But the problem is it's too slow. It's too slow even using the most powerful supercomputers out there right now, like the supercomputers at Oak Ridge and at Argonne and at Berkeley. Simply, it takes too long to run. If it takes too long to run, if you're interested in applying these simulated results in real time. And this is a big deal, that not just in fusion, but in many different areas, you want to have validated sorts of codes, which means it has to demonstrate that it measures up in terms of checking against observations and such, but it has to be executed very quickly. And an example of something that we had to do was to work with this state-of-the-art global PIC code that ran on all the supercomputers around, but it was too slow. And so how do we do this? So this says SGTC, which means synthetic GTC simulator. It's a very fast simulator, and it's the associated predictive workflow. It's probably too hard to go through this in great detail, but it's quite interesting. The SGTC simulator here, which is just recently published in Nuclear Fusion Journal, it basically outputs the plasma control for real-time MHD instability control for the larger MHD type signals. The SGTC outputs other predictive algorithms of FRNN type models as input or real-time simulators. And this is really very, very promising because you're executing this on a very, very rapid time scale. And it gives you the germ for interesting some of the top industry people in working with us to develop digital twins for disruption prediction and control. Let me skip to that real quick here. So this SGTC real-time simulator leading to a Tokamak digital twin, the motivation is that you need this for predictive guidance, since two things here. If you look at these two bullets here, observational data is unavailable for design devices important, such as ITER. It hasn't been completed yet. So how the heck do you predict with confidence moving forward and be able to exercise this in real time and be able to manipulate the plasma state, as we've been talking about through this discussion? Experimentally validated first principles HPC codes, and I just gave you a little snapshot back here of this is GTC, which is just great. It's fully electromagnetic now, but it takes too long. And so SGTC established the workflow of neural network-based surrogates, the experimentally validated first principles electromagnetic gyrokinetic code, GTC. It was trained with extensive simulated data from GTC itself, taking as input equilibrium states that D3D was studying that were ITER-like states to carry key physics information. And so here's the takeaway here. These SGTC models satisfy compatibility requirements for a plasma control system and can deliver inference times on the order of milliseconds. This is pretty amazing. And SGTC can deliver results, and I emphasize this, 5 orders of magnitude faster than GTC runs on the fastest HPC LCFs. And that's why the big leadership class supercomputing centers at DOE, both Berkeley and both Oak Ridge and Argonne are very, very interested in coupling to our activities in this area, because it gives a very solid reason for their continued growth. So so what does this lead to? Because if you now have this, which is at least, I'm not claiming at all, it's crazy to oversell things. We're just on the threshold of being able to deliver these sorts of capabilities in a way that our experimental colleagues that sit in the control rooms would say, well, yeah, this is useful. But you're doing this too to really probe the advanced operating conditions for plasmas that haven't been achieved yet. And so one way that you can move this forward rapidly is with these digital twins. And here, let me say a few things about this. The NVIDIA Digital Twin Tokamak project involves NVIDIA's deployment of their Omniverse visualization capability, and it involves the integration of the CAD files from the actual D3D experiment. And it also allows interfacing at least elementary versions of the EFIT code, but as I've said before, the capabilities and such will make that continue to improve. The digital twin development will clearly accelerate fusion engineering in the same way that it does for the design of complex systems. Fusion is not the only area that's doing this. As Professor Karen Wilcox at University of Texas at Austin, and by the way, when I mentioned these AI for science and security meetings, Karen gave a really nice plenary talk about digital twin work in aerospace engineering at the first of these AI for science and security invitation-only meetings. This was held in Knoxville, Tennessee. And this is a link to more details from it. But as you can see, this is, we're really realistically moving forward with this capability now. The NVIDIA Digital Twin Tokamak project involving this omniverse integration of all of these elements is very exciting. And the other thing that's very encouraging from all of this is that the NVIDIA people are putting their A-team visualization people on this because they see the potential for real impact. And here we've actually taken this SGTC AI surrogate near real-time simulator and put it into this integration of the D3D CAD files, the EFIT boundary and coil configuration. And these are some results from this that are just coming out. And this is a collaboration involving NVIDIA, Princeton University, and GA. So this is something that I'm not sure I'm allowed to show this right away, because I'm also involved in putting together a DOE AI for Science and Security report that will be coming out near the end of this year. But I wanted to show this to you all. because this is a AI for science and security roadmap. This Rick Stevens at Argonne came up with this sort of template, and we don't have to go through this in great detail. But what Rick and colleagues at Oak Ridge and such asked me for was to put this together in this roadmap with the fusion energy exemplar. What would you do? And in particular, if you look at this, we're here in 2022. So what's the current state of things? What will you be able to do in 5 years, 2027? What will you be able to do in 10 years, 2032? What's your vision for 2037? And here we label these here. So in the current state, the current technologies enable us to carry out experimentally validated HPC-enabled AI machine learning on prominent facilities like D3D and JET. But in 5 years, what do we hope to achieve? We hope to achieve more foundational research with an experimentally validated digital twin on leading facilities worldwide. And if we're able to articulate and also demonstrate clear progress in this area, and at next the big SC22 conference that's coming up in Dallas, Texas, within 2 weeks, I'll be meeting with several representatives, if you will, from the international facilities, because one thing you have to be clear is that outside of D3D, the US is not producing fusion-relevant tokamak data. So you have to rely on productive international collaborations. And yeah, there are various things you can chase, different concepts and such, but to have the level of ground truth information from tokamaks, you don't have time to do all of that. And so you have to rely on international collaborations. And so what does this lead to 10 years out? We believe that the long-term goal will involve the design of a fusion pilot plant using validated models. We'll see good progress in this capability. And the 15-year horizon in terms of transformative science will be to construct and operate an actual fusion pilot plant. And this takes you out to the mid-2030s, which is what US Secretary Granholm is saying this should be the goal for the US. We can't afford to sit around and wait. And so this is maybe it's a little too dense, a slide, but what we try to capture here is magnetic fusion energy as a 21st century grand challenge that requires very solid interdisciplinary research. In other words, you can't do it just with physics alone, applied math, so on and so forth. It requires a lot of engineering and a lot of validation. So it involves validation against large observational experimental databases for prediction and real-time control. It involves the engagement of real-time simulators, as we've been talking about, backed by first principles-based leadership class facility codes. Industry engagement. This is very important. Secretary Granholm was very, very stimulated by seeing the level of venture capital and startup activities in the billions of dollars invested in fusion. And this doesn't necessarily have to be doesn't necessarily result in a completely optimistic outcome, because the engagement of startups and things can also lead to a lot of promises that can't be fulfilled. And that's the last thing fusion energy needs, is a lot of promises that are not fulfilled. But these are pretty solid in terms of the engagement of really heavyweight industries in this kind of AI type activity, because we have very productive collaborations with Microsoft. Everybody's heard of Microsoft. And so Microsoft's transformers are very, 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 very promising, because it accelerates the rapid transfer of large multidimensional complex temporal data, and at levels that we haven't really tried to do before. Because as I said, remember what I said about what we did with the Nature paper and then translating that to real time. We're dealing with ground truth measured data for 0D and 1D time traces. We didn't do 2D higher dimensional data, but the transformers give great promise of being able to do this. Large volumes of temporal multi-complex data. And turns out that Microsoft and NVIDIA are both interested in this, and they're coordinating some of their hardware strategies to be able to do this. So this is a real substantive thing. This is not science fiction or anything in terms of, well, we hope to have a big player like Microsoft interested in what we're doing. And then the other part of it is, as I mentioned, NVIDIA has a big investment. Their CEO, Jensen Huang, has a big interest in their fully three-dimensional visualization capabilities, a real omniverse or virtual reality capability to deliver near real-time three-dimensional images with CAD files and simulator models of the type that I mentioned. And so, you know, these people are already engaged with us and with their frontline people. This is not, this is no joking matter, because this doesn't cost our people, the DOE funded people, a nickel. They're putting in their own resources in this area. NVIDIA has supplied us with hardware, these A100 GPUs that through their collaboration with us, we are able to bring that to the D3D facility. And we are exercising right now a very, I think, important development where, again, the NVIDIA people are helping us demonstrate that with GPUs, that, in other words, welcome to the 21st century fusion, but CPU-driven plasma control systems can be improved with GPUs. This shouldn't be a big shock to anybody, but we're going to carry out real-time simulations in the plasma control system at D3D with the aid of Microsoft and NVIDIA, with NVIDIA really tracking this very carefully, what's coming up. And what is the essential role of AI? Let me highlight this again. AI is what enables you to run large ensembles of simulations on leadership class facilities and be able to exercise uncertainty quantification. These are be able to quantify more the error bars around what you're predicting, and the interpolation of parameters. What do I mean by the interpolation of parameters? Well, if you're able to project forward in a realistic way, then you can use, for example, like with these powerful simulators like the SGTC, you can project forward to interpolate possible developments that you can't out of just the ground truth measured data. And so that is a very exciting element. We accelerate real-time development of simulator and surrogates for active control and design. This is very clear. You can't do this without AI. And you also have to address the hardware computer science challenges for having a controller on the edge, or what they popularly call computing at the edge these days. But for fusion, it's controlling the physics in the edge region in an intelligent way. And then I underline this another essential role for AI. Everybody has difficulties these days attracting and retaining best and brightest young talent. You know, people complain like mad, oh, well, you know, Google, NVIDIA and such are scooping up the talent and we can't keep everybody. But, you know, that's not entirely true. You can do this, attract the best and brightest talent for this stimulating growth area, if you give them something to stimulate them. Very talented young people, and I can vouch for this. They come to my project at Princeton. These are premier Department of Energy computational science graduate fellows. They can go anywhere they want. They're fully funded to go wherever they want. They want to see something exciting that they can learn from, that could lead to career tracks, or it could allow them to move into other areas. You have to be able to do this. Otherwise, you're not going to, just by, as I say to my Princeton University colleagues, that throwing the Princeton University designer logo on the table doesn't do anything these days. You have to offer them a lot more. So the delivery of abundant clean energy requires AI for science. This is well subscribed to. You're going to see a lot more of this from DOE, but NSF is already up and running in this area. Multidisciplinary R&D is absolutely essential. It can't be just one particular type activity, can't be physics alone, applied math alone, and so forth. It is truly multidisciplinary with a big engineering component. Industry partnerships, so that, as I just mentioned, Microsoft, NVIDIA, we also have active engagement with Google at Princeton and also Intel for the AURORA activity, and strategic international collaborations. I put an exclamation point because the US in the fusion grand challenge here is data poor, facilities poor. You have to couple to, on the pathway to ITER, you have to couple to other facilities like JET, like the Japanese JT60SA. That's going to be a machine, superconducting machine, the size of JET. And but because of Fukushima, they can't do deuterium tritium, but having a long pulse steady state device, which is a prototype also for what ITER will eventually deliver, is tremendously valuable. And it enables a lot of ideas from the AI for science area to be tested. So this is my last slide, and it's a cautionary. The US cannot afford to lose the international race for clean fusion energy and AI. There's a lot of competition out there for obvious reasons. You can't afford to do this. And there are areas where we're already lost the international race in other areas. And this is extremely important. Clean energy, fusion energy, and true meaningful AI advances. But to end on a positive note, the future is extremely exciting for fusion and for AI. And I again thank Frank, and I look forward to discussing with people here in San Diego a lot more details and stimulating discussions during my visit here. So thank you very much for your interest and time.
Is this on? Hello? Hello? 1, 2, 3. Yeah, now it's on. Any questions first from outside? Anybody have a question from the outside? Just unmute yourself. If there's a question from outside. And then inside. Anybody have a question from inside? I have a couple of questions. You indicated that there is, in essence, and I understood it, 2 time scales. One is the time scale of actually within a shot, controlling against instabilities. And what is the time scale to know what to do next in the next shot? I was curious for the first one, for the time scales within a shot. What stops you from doing what you described 24/7 routinely on D3?
No,
you mentioned that there's 200 shots were made. I forget when exactly. What stops you from doing this for every single shot?
Well, first of all, the temporal range for actually being able to control the plasma state varies, so it's a very good, deep question that you're asking. So the time scales that you're looking at are different time scales. So that if you're looking for an immediate sort of response, to prevent something nasty from happening, that's analogous to like an airbag in a self-driving car. Okay, you don't want to be exercising the airbag all the time, you know, but it will protect the driver, and for the most part. So you have to be able to, and that's what the self-driving car industry is all focused on in real time, to be able to pull back in time to look much earlier in the evolution and be able to focus on events that you can control more as you do. And these take on different time scales and such. And so you have to focus on the targets that are validatable and such. And that's what we're talking about here. A lot of this is just kicking off in a significant way. And the starting point, Frank, is that, you know, before there's any confidence that the experimental facilities people will embrace activities of this kind, that's why that Nature paper was so important, because we dealt with a lot of archival data, you know, that of real ground truth measured dynamics, that where you could observe disruptions, and this both at D3D and at JET, and this transfer learning was demonstrated. This is all with archival data, but you could do Gedanken experiments with that too, right? I mean, you could say, all right, and this could be applied to other areas like climate predictions and things too, where you have archival data and say, well, how good is your prediction really? You know, if we just do a Gedanken experiment and see what you're doing, you know, in terms of being able to control things. But it takes on different time scales in doing these things. And the real excitement is what do you do if you're able to, as we were able to be able to use these AI enabled inference engines to be operating in real time. And that hasn't been exercised as widely as we would like to, because in other words, I'm not going to be glib about this, Frank, and just say, well, we know all the answers to that. We could just run the machines a lot and exercise these things. We got to be learning these things as we move forward in seeing what sort of time scales we can capture.
There is a question from Yifeng. Online, thanks, Bill, for the nice presentation. What is your experience of running GTC on Crusher and OSCF? And the outlook of the currently coming year, any progress made along the roadmap with SysTickle and 1API on Aurora? Basically, what's the situation on running these simulations?
Yeah, I know Yifeng's question is very welcome, and I know Yifeng from before, and I will see him here on Wednesday. But he's asked a very good question. He's saying, how does it look for running SGTC and such on the exaflop system? And the lead-in to that, he mentioned Crusher, which is the existing lead-in machine that Oak Ridge is running before they can actually run Frontier. And we are well coupled to that right now. And we've done a lot of benchmarking tests and such. And so when the real machine, the Frontier machine is unveiled, the fact that as Yifeng is mentioning, it's absolutely necessary to do some benchmark testing on Crusher, which is the system that will lead into Frontier. And I've been in a lot of discussions with the leadership at Oak Ridge, with Doug Cothey, and also with Bronson Messer, and they're very encouraging. They basically say, yeah, let's you know, take the harness off and try these things out. And because it's in their best interest, if we can demonstrate that these state-of-the-art AI for science simulator capabilities, which have a big impact on the future for real-time control, can be demonstrated on their leadership facility. So that I think that should be very exciting.
Any other questions from the outside or inside?
Hi, Bill.
Hi.
Exciting talk.
Hey, hi.
I just had a quick question on your roadmap. You mentioned the plans for the AI and for fusion predictive design in the 10-year time frame with then informed operations in the 15-year time frame.
Yes.
Is that enough time between there for predictive design to inform those experiments, or is that for something even further down the road?
Yeah, that's an ambitious goal, you know, that we're trying to set. And whoops, anyway, I was going to show the slide again, but we want to demonstrate that capability, and to do that, we need all of these different elements that we're talking about. And I think we have some credibility in being able to move this forward, because the industry people who, you know, they're not your buddies or anything, you know, they look for the bottom line, and they want to see, as you're developing these capabilities, why should they put their labor into this thing, invest hardware and actually invest a future operating time on various things. And so that's why I'm cautiously optimistic we'll make progress on this. And the digital twin thing, I think, is really interesting, because this is a virtual reality capability. And you can imagine, right, that if you had a realistic virtual reality thing, not the sort of thing that Jensen Huang can show in his wonderful presentations and things, but something that's really realistic. That because then a project like Eurofusion Jet, which is very unfortunately, I didn't mention this, although the science ministers and everybody were saying, this is great, you know, this gives us motivation to really invest in fusion. They're calling an end to the operation time of that sometime in 2024, because it costs a lot of money to keep it going. But it's the only DT machine that's running until ITER arrives. And there's a big gap there. And so I'm in the process of discussions with them about accessing their database, which will be much longer. And this is why, maybe a little long-winded way of giving you this explanation, but being able to do a digital twin for Eurofusion Jet would be very, very exciting, okay? And give more credibility, if you will, and maybe give ammunition to Tony Donnet, who's the Director General of Jet, who made this pitch to the European science ministers to extend Jet for 10 years. And they said, no, you know, oh, that's too expensive. You need it for other things. But the thing is that you know, once you destroy a multi-billion-dollar facility like that, that's well diagnosed, that's a huge, huge loss. And so in a Zoom call that I had with him, you know, within the last couple of weeks and such, I said, maybe we can help, because if we can deliver a realistic digital twin for Jet, this is something you didn't pitch to the ministers before. And this is something that Jensen Huang would be very happy to see done, you know, where you can demonstrate, hey, this is a virtual reality thing, but it's not bullshit, you know, it's been validated against a lot of things, and it's continually improving. And if you have something like that, and the NVIDIA Omniverse A-team people are continuing to work on this thing, and we'll be talking to them at Supercomputing about how much they can improve this still. Why are they doing it? They're not doing it for charity, because this is advancing their product, you know, this visualization capability. But at the same time, and the other industries and such, like I had a good discussion with the lady that that gave the plenary talk at the AI for Science meeting in Knoxville, Karen. She said, you know, when she really made a lot of progress in aerospace engineering deployment, including impact on drones, which are real-time sorts of things, that being able to deliver digital twins for this is a wonderful way to communicate, you know, about not something that you have in the bag, because that's not, it's still virtual reality, but it gives the funding people a lot more confidence. So I hope I've tried to answer your question as best I can, but it's evolving.
Any other questions? Otherwise, let's thank the speaker again.
Thank you, Frank.